All right, good afternoon, everyone. I'm going to get started here in a couple minutes here. So if you're still getting yourself situated, no worries. We'll get started at about 5 after, so about 3:35 for those of us on Eastern time here in the U.S. We'll get picked up around then. What I want to get started with is we're going to pick up right where we left off yesterday, and I want to really spend a lot of time today getting exposed to different meshing techniques, different ways we can mesh various different parts. And that's going to really be our big focus today is element creation and how do we judge whether we have a high quality mesh or not before we kind of really wrap up the model building steps today. And that's going to put us in a good spot for our final session later this week to cover analysis setups and actually defining the physics problems at hand that we're looking to solve. So we're going to just wait out another minute or so here just for any last minute users that are still getting themselves joined into the session or anyone else that needs to maybe grab a quick cup of water before we get started here. But it gives you guys another minute or so, and we'll kind of pick up right with our 2D meshing lesson that we kind of paused on yesterday afternoon.
Excellent. Thank you, Garrett. And sorry, I joined a couple minutes late here. Again, hopefully everybody had chance to review the material we gave yesterday, and also if you do have a couple questions you wanted to ask, please put them in the question tab, and I'll either answer them, or if I need to, I'll reach out to Garrett to help out with those.
All right, folks. So for the interest of time here, I'm going to get started here, Darius, unless you have any reservations.
No, I do not. I'll hit the start record button so we can capture everything here. So again, looking forward to day 2.
The broadcast is now starting. All attendees are in listen-only mode.
Let me pull this little Mr. Monitor up. There we go. Okay, so yesterday we had left off. We spent quite a bit of time yesterday talking about why we're going to need to make a mesh here, and we'll remember from yesterday that really just came down to this idea that on its own, a CAD file, when we're reviewing it, doesn't necessarily tell us a lot about the stiffness and the mechanical behavior of a part itself there. And we learned yesterday that what's really happening in a lot of FE simulation, especially in the structural domains, is that we're really just solving a fancier version of Hooke's law for an ideal spring there. So knowing that we're kind of doing a much more advanced version of F equals KX here, we want to start kind of thinking of this in terms of this idea of a stiffness matrix for a lot of our parts there. And I know that seems a little vague and ambiguous and maybe more than we signed up for there. But at the end of the day, the reason why we're concerned about that stiffness matrix is that's going to be really what's driving the results that we're going to be getting. That's responsible for making sure we're representing the parts that we want to model in correctly and as accurately as possible. And really, though, it's the mesh and the elements that we're creating that are going to have the biggest influence on how that stiffness matrix is being created. And as a good rule of thumb, we can carry with us from today moving forward that as long as we have a high enough quality mesh and we've set our materials and properties correctly, we should feel pretty confident that we have a digital twin or the virtual twin of the part that we're trying to represent in our HyperMesh model. And it's so really what we want to make sure today is not only that we're generating the appropriate mesh with the correct elements for the situation at hand. So we're going to talk about a couple different models today to get exposure to different element types. But we're also going to learn about what makes a good mesh actually a good mesh. And you're going to hear me say over and over again, like I've done yesterday, this idea of an apples to apples comparison. That's really what we're looking to get at. So you're going to hear me say that quite a few times this afternoon. And I think once we kind of have a bit of exposure to some different situations and different parts that require different, mesh requirements, I think that's going to really tie together the big picture of why we again need to mesh in the first place, what are the benefits of taking this approach, and hopefully that kind of knowledge should be really helpful for us moving into our last session and later in the week together there. So kind of a nice little hands-on day. And what I like here too is certainly, feel free to pull up these models and click around a little bit while we're going through them. But I think today's a really good lesson where whether it's tomorrow or, even next week or a month from now, even when you have some time to, go through some of these exercise models and click around and try to mesh through these yourselves there. So I think we're going to see some good practical exercises and things that you guys can kind of practice with or fool around with and sandbox with while you're getting familiar with these tools on your own. So before we go too far, what I'm going to do is steal my my student PDF file that some of these slideshows that we were stealing from yesterday. And I want to talk a little bit more about that AutoMesh tool, what's going on with it, and how we can maximize it once we kind of get familiar with the specifics of it. So we saw yesterday, we blow this up just a little bit there. We saw yesterday that when we're meshing, I mentioned at the end of the class that we'll typically mesh a surface from its edges in. Now, there's nothing specific that we have to do for the most part for this formulation to work. It's just kind of the HyperMesh logic at play. But as a result of that, we're typically going to be concerned with, while we're meshing, concerned with the number of nodes placed along a given surface edge. So for reminders that we typically mesh surfaces at a time, and those surfaces get meshed by starting from the outside in. So we're going to be concerned with these node densities or these element densities along an edge while we're meshing. And that's kind of the big thing we're going to want to keep an eye on while we're going through this. Now, what's really great about the meshing tool, though, is it is considered an interactive tool. And if I kind of scroll down here, keep coming just a little bit, we have this idea that the tool itself is interactive, and what we're actually going to be adjusting is those node densities along the edges. So when I say that HyperMesh allows you to, in sort of real time, make adjustments to your mesh on the fly, that's specifically the most common way we'll adjust a mesh typically, is by incrementing up or down from 6 to 7 or 4 to 3 elements along a specific edge there. And I'm going to leave it actually here on slide 16 for a moment. We'll come right back to that. So I'm going to come over to my heat shield or the Batmobile component that we had to work with. And this is what I want to use as kind of my sample component for now. Now, we learned from yesterday that this is a simple 2D surface mesh or surface component. So there is no thickness to it. It's already as if it is a mid-surface from maybe another parent geometry file not present. That's all right. We're going to learn today that whether it's a 3D part or simply a 2D part, just that flat surface there, our surface meshing tool is going to behave the same and allow us to still work with that part. There's going to go to some of the other extra steps we can take with those meshes once we get them done there. So what I can do here, let me get my spotlight tool here. What I want us to be concerned with for a moment here is we're going to remember that we have the panel area on the bottom of my graphics area. And I'm going to want to switch this to be my 2D menu with that little radio button there. And once I got that set to the 2D page, I'm going to come to my AutoMesh tool on that second column to the right there. Now, we can also access the AutoMesh tool. We learned yesterday the F12 shortcut key will bring that up there automatically for us. And what this allows me to do is simply select surfaces to create a mesh on, and I'm going to provide the surfaces as input, as well as specify the average size and the element shapes used to create that mesh. So let's kind of see this in action together for a moment here. I'm going to zoom into my part here, and you'll see that the view's been adjusted to what we refer to as a by 2D topology. We'll talk about that a little bit more with our 3D meshing later this afternoon. But for now, I kind of like it though, if nothing else, just because the edges are easier to see now that they're this almost this neon green color here. So what I can do is I see that my panel's requesting me to provide surfaces as input. So we'll remember from yesterday that yellow panels require graphic input from the user. So it's asking me to give it some surfaces. I can come over with my mouse and I can left click just to add in some of these surfaces to the selection. And I'll just grab maybe a dozen or so to start here. Just this little section right here. And also remember that we can right click to deselect from selection as well while we're going through this. So no need to panic if you accidentally select the wrong things. So right now I'm letting HyperMesh know that I want to mesh these 12 or so surfaces together. I'm going to be meshing them with, let me get my little spotlight tool here. The middle of the panel has an element size field that I can type in a numeric value for. So right now I'm just setting it to be 4 millimeters. And I'm going to use a mixed mesh type for now. That's going to be a combination of quads and triads. As a rule of thumb, I mentioned this yesterday, I don't want us to be afraid of tria elements. And some of you might be thinking to yourselves, well, he keeps talking about this idea of having an apples to apples comparison during its mesh. I don't really know how I feel about comparing stresses in a square compared to stresses in a triangle. Doesn't that get away from this idea of apples to apples? And you're not wrong for feeling that way, but really what we come down to is we'd have two options at that point. So we're going to play a quick game of Pictionary together here. In some situations where a surface is really getting tapered down to a smaller edge length, so maybe something like this here, this kind of trapezoid shape, yes, I could, include this kind of taper lines in here to easily have 4 rows of elements, row 1, row 2, row 3, row 4. And if I do it with this approach, it's pretty easy to see how we can grid this up and have just, square cubes or rectangular-ish cubes left behind. But the problem with this approach is that depending on how big the edge length at the top, like 1 up here, compared to kind of E2 at the bottom, if this second edge length is substantially smaller than the edge at the top, well, it doesn't make sense to have the same number of elements on the top and bottom. At that point, what I'm really modeling is, sure, we have 4 nodes on top and bottom. That's the same number. But really what I've just done there is I could be modeling this with elements as small as, 2 millimeters at the bottom, since this is only an 8 millimeter long edge. But if the edge at the top is something as big as, 80 millimeters, well, then what I've really just done there is mesh something with 20 millimeter elements on the top of this little surface and then 2 millimeters on the bottom. Pardon the poor drawing, but the idea behind here is at some point we have to make a decision to ourselves, is the average size of the element more important than the shape? And frankly, I think that should be a bigger target for us. Now, we're going to learn today that we're not always going to be 100% perfect with truly identical elements where they're the exact same shape and the exact same size, but that's the goal. So if having the occasional tria element helps us ensure that our elements are the same size, that's kind of a necessary evil in order to get that requirement there, that our elements are the same size. So in my opinion, you're better off always comparing elements of comparable size, even if you have an occasional tria involved, rather than introduce huge variance across your element size, but at least you were able to keep quadrilateral elements in that case. So in my opinion, trias are really kind of a necessary evil to manage some of the surfaces we're going to run into, and we'll kind of see some examples of that together in a moment here. So what I've done here for now is I got my couple surfaces selected. I'm going to mesh it with an element size of 4 millimeters with a combination of square and tria elements. So I'm going to go ahead and hit the mesh button here. Now we're going to see this kind of neon green mesh pop up here, and this lets me know that it's kind of penciled in, but not finalized. We still have some chances to come in here and interact with it and adjust it. Now, Darius had mentioned at the end of our lesson yesterday that a good way to assess your mesh quality is first by checking with the old eye test, and that's a very good way to go about it. Now, we're going to learn about some more technical, mathematical definitions of a high-quality mesh, but to be honest, generally, if a mesh passes the eye test and it looks aesthetically pleasing, it looks, like it has artistic value in a way, you're probably on a good shape. You're already on the right track, rather. So what I mean by this here is this is a good example of where we can use some of that eye test to adjust this mesh here on the slide. So I want us to pay attention to here. I'm going to bring up my spotlight to help out. Now, if we look at this top surface fillet over a couple surfaces here, I have about 4 elements along this first edge, another 32 or so that go along the long edge. And then once we get down to the more radial direction of that surface fillet, on the left side, we have 3 elements. I have 1, 2, and 3 making this up. And on the right side, I have 1, 2, 3, and 4. So let me kind of exaggerate that a little bit here. What I'm going to do is I'm going to back out of this and just mesh that surface fillet for now. So like I was saying before, we have 4 elements in the height direction. So if I really zoom in here, we have 4 going 1, 2, 3, 4 from top to bottom. But as I zoom back out and come over to the left, you'll see here somewhere along the middle of the surface where this triangle is, we're going from 1, 2, 3, 4 on the right of it to 1, 2, 3 elements on the left. Now, why that's the case is probably the auto mesher detected a difference in length between the edges on the left and the right. So the edge on the right was probably a little bit bigger, and as a result, it wanted to use more elements to account for that increase in size. But I'm sure some of you are kind of looking at this and thinking, well, here I'm not getting that apples-to-apples comparison. And that's true to an extent. What we're modeling here is a fillet that's sort of done with 2 different approaches on the same part. One of the things I'm going to kind of preach to us today is this idea of mesh uniformity. And in my mind, there's really 2 big ways that we can achieve mesh uniformity. All of my elements look roughly the same and are roughly the same size. So from an element to element perspective, we want them to be as uniform as possible. And then the other part of it's more of a macroscopic way, a little bit more global, in that all of my identical or repeating features on my mesh are meshed the same way as they repeat. So what I mean by this, don't model, a given half-inch hole with 8 elements around one time, and then another way with 4 elements around. You know what I mean? So we want to make sure that if we have, the same feature over and over in the part, we're modeling it the same way within the elements over and over again. So why I bring that idea up is let's come back to the fillet here. We're modeling half the fillet with 4 elements in the radial direction, the other half being modeled with 3. That's a big inconsistency right there. When I get to my results in post-processing, I wouldn't have as much confidence that the results on the left half correlate with the results on the right, knowing that they weren't meshed the same way. So what's great about HyperMesh is now that I have this sort of penciled in, this neon green view, to fix this, it's just a matter of zooming in. And we're going to hold control. I'm going to zoom into this edge here. And what I can do, I'm going to kind of just zoom in here. I'm just going to left click the edge. And as I left click it, it's going to increase the nodal density. So now it's letting me know it's going from 3 to 4 elements at that edge. And now I'm just going to hit the green mesh button to repeat that mesh operation. We're going to have it retry again with the new density settings that I've set there. And now we'll see that it went from 3 to 4, 1, 2, 3, 4 elements in that radial direction. So if we zoom out and kind of look at the middle of that surface there, I'm not seeing that triangle element introduced anymore because the node density on the left edge to the right edge matches there. So really, trias tend to be introduced on surface meshes to account for a change in element density along an edge as it traverses over a surface there. So as long as I'm making sure those elements densities are identical, we're going to see a majority or an exclusive quad element mesh while we're going through it there. And that's really what we hope to see, is more quads than triads. Now, we're going to see there's some surfaces where it gets really tough to be quad dominant, and that's okay. Now, typically, you'll see more of those transition areas in surfaces that aren't as boxy or square shaped, or where there's a big change in dimensions from one edge to another. So I want to take a look at the fillet coming up on the part over here, where it's going to have a bigger outer radius than it would inner radius due to the fillet nature. So I'm going to kind of just use a little selection here to help me out with this. See if I can highlight the edge that I'm referring to. So that's all right. Yep. The edge over here that I've just selected and kind of turned on and off, that I keep clicking and it's flashing, that edge is going to be a little bit shorter than this edge underneath it that I'm now clicking and flashing, because that edge is a little bit longer due to the fillet there. So why does that matter that one edge is longer than the other? Well, this is like that trapezoid scenario I was trying to draw for you guys earlier. Because the outer radius is larger than the inner radius, it's going to want to mesh it with some triad elements. So actually what I'm seeing here is this surface is meshing in a way where it's going 8 elements on the exterior, trying to taper down to 5 elements. Now we have a couple options here as meshers. I can either leave it exactly how it is, and the benefit of doing so is that I'm ensuring the elements are as close to the same size as possible. And frankly, that's something that I'm a big fan of doing that there. Now I could also adjust the element densities though, and it might resize the elements a bit, but it can help ensure that I have a clean quad dominant mesh. So maybe what that could look like is I'll left click the top edge to increment it from 5 up to 6. So left click to bump up, and I'm going to come down to the bottom edge and I can right click to decrease that element density down to 6. So now I have the top edge got bumped up, the bottom edge got bumped down, and now I'm going to hit remesh, or just the mesh button again rather, and now we'll see that it meshed it with a perfect 6x4 sort of grid over the fillet. Now, one thing to keep in mind though, is that we originally meshed this with the mesh size of 4 millimeters in mind. We used, in this case, 4x6, 24 elements to cover that area. If I bump this down to be, even a 4x4 grid of elements, yes, it still looks relatively clean, but keep in mind that as I decrease that element density over the edge, I'm increasing the element size. The area that needs to be covered by squares hasn't changed, just the number of squares. So as a result, the squares themselves need to get bigger, or the elements need to get larger if I'm going to choose to use less of them. So why I bring that up is you want to be a little conservative by about how much you're incrementing these edges. If you find yourself that HyperMesh with your given element size wanted to mesh something with 20 elements along the edge, I wouldn't try to go as low as, 5 elements on the edge or only 25% of it, because that could really start to substantially increase your element size. And the concern for that we know now is we want to make sure our elements roughly look the same and are roughly the same size. So there's a bit of a balancing act to it, but hopefully what we're seeing is that at least the tools to make these decisions are very quick for us. It's just a simple click here and there, and then you can just remesh it again to get that updated mesh body there. Now, one thing I saw yesterday, and this kind of gives us a great opportunity to think about this. A question I saw some users had is, how do I determine my average element size? I'm ready to mesh my part. I want to start these FEA simulations, but I don't have the instructor sitting here next to me telling me to mesh something with 4 millimeter elements or 10 millimeter elements or 1 millimeter elements. What are the decisions that go into that thought process there? And how do we make those decisions there? And really what it comes down to, determining your element size, is what features do you want to capture? So let's talk about this next here, determining my element size. So the questions that you should really try to ask yourself, the first one is, what kind of results do I want to see? Are you looking for a deflection of a particular edge or surface, how much it gets pushed back or bowed out as you load the part? Are there stresses that you want to see? Do you want to see a stress at a welded interface where you're seam welding two things together and you want to make sure that weld will hold up? Is it a durability thing where you want to make sure the life of something will hold up there? You got to know what results you want to see, and more importantly, where on the part do I want to see these results? That's kind of the other half of it. Where on the part itself are you going to be zooming into on post-processing day to review those results? You know, where exactly are those critical locations that you're interested in? And it's important you ask yourselves these questions first, because everything is going to be results-oriented in a moment here. So as a rule of thumb, determining your average element size, the goal is to get as large of an element size, in my opinion, that still allows me to capture my smallest feature of interest. So why do we want to use the largest element size as possible? Well, we learned from yesterday that we're doing Hooke's law for every given element in our part. So the more elements I have, the more physics that need to be processed, which means a longer runtime. So the less elements means quicker results, which is generally more reliable. But we also don't want to just have so few elements that we don't have an accurate part anymore. And a good rule of thumb to determining if you have a small enough element is to compare it to your smallest feature of interest. And how do you know what a smallest feature of interest is? Well, go back to your first two questions. Is it somewhere that you're going to want to see results at? So let's take a look at this heat shield together for a moment. And we're going to make up a fancy situation together. What I want to be able to do in this next mesh is simulate a situation where, if I were to take another screenshot of this guy, I want to load the part on this surface over here, kind of this bottom table. And I want to do the same thing on that back side as well. I know we're not seeing it, but there's another little line there. So we're going to kind of load those two phalanges here. And I want to see this thing start to bend in the middle there. So some things that are probably going to be important for me in that kind of simulation, where we're going to be trying to bend this little kind of top plateau, is I want to make sure maybe these fillets are modeled in correctly and accurately, so that way I can see the stresses form in those fillets. And I want to feel good about my stresses when I'm looking at them at those filleted regions there. So what I would do is I would always start with my smallest feature of interest. And in this case, it's going to be these kind of fillets between the different planar sections of the heat shield. So let's just say for argument here, and actually we don't need to say for argument. What I'm going to do is I'm going to come into my HyperMesh tools and I'm going to back out and go back to my geometry menu. And yesterday we saw we had that length tool. I'm going to take my little length tool and I'm going to measure the radial edges of these fillets. So I can see one of them is about 10.5 millimeters in that length. I got another one above it that's roughly 13 millimeters or so. And on the back side, the upper radius is 17, followed by a lower radius of 7 millimeters. So of all of those lengths, 7 millimeters was actually the smallest fillet there. So let's say that 7 millimeters is our new feature of interest. So we saw we had like 17 mm, 13 mm, 10 mm, and 7 mm fillets there. Let's say that 7 mm is still considered a critical feature. That's the smallest feature of interest. Some other features, though, that can come up that you build these things around. So in this example, we used a fillet. So fillets, the rule of thumb we're going to see in a moment is you need to fit 3 elements or more, generally, on a fillet face. For holes or washers. And for even a part thickness direction, which we'll see in our next example, we need at least 3 elements there. So what did I really just do there? Let's kind of take a step back. So we were talking about determining our average elements together. And how I like to go about this is first deciding or getting an idea of the results I want to see. So in this example, I'm curious about seeing bending stresses forming at those fillet locations if I were to compress the part at both the left and right side and kind of crimp it together. And I want to see, like we mentioned before, those stresses specifically at all of those surface fillets there. So I measured all of my different surface fillets. I have one that was as big as 17 millimeters and another one that was as small as 7 mm, or, not even a half an inch there. So that's pretty small there. Now, I still want to be able to see accurate results in that 7mm fillet there. So in this example, I'm going to use that as my smallest critical feature. And now the final step is just determining its mesh appropriately. So we're going to learn today that a good rule of thumb for meshing fillets is to ensure you have 3 elements in that radial direction. So again, we're going to be adjusting those element densities like we saw to make sure we have at least 3 elements in a fillet. Or we're also going to see that for some things like a washer hole, you might want to make sure you have 6 elements forming around the hole in order to both capture the geometry correctly and give yourself accurate sampling points there. So let's actually see this in action. So I have a 7mm fillet, and I want to be able to fit 3 elements comfortably on it. Well, I'm no genius, but I do know that if I take a little calculator here, I can just truly take that 7.1mm fillet, divide it by 3. That gives me an average element size of about 2.4 mm or so. So what we're going to do is just bump that up a little bit, and we're going to use a 2.5mm fillet here. 2.5. So I'm going to come back into my meshing tool, and I'm going to change that element size to be 2.5mm. And while I'm doing my meshing itself here, I would never recommend, especially for parts that you're really concerned with, just grabbing all of the surfaces and meshing them in one shot. It'll work. There's a lot of logic built into HyperMesh. It's not going to give you terrible results, but I really think you're doing both yourself and the product a disservice by just grabbing everything and just throwing a quick mesh on there. Yes, it'll work. It won't be terrible, but there could have been some other things along the way that we could have probably improved. So I would not recommend going about that. But instead, one thing I like to do is take a handful of surfaces at a time and, maybe mesh a dozen or even half a dozen just at a time here. So right now I've only selected about half of that top fillet, that 17mm fillet on this side. I'm just going to mesh that. And now I'm just going to come in here for a quick review. So I'm seeing on one edge here, we have one triad element introduced as we're transitioning from 18 to 17 elements. I'm just going to right click the 18 edge to make it 17. And now I see that it's nice and clean. I'll move on. The next couple fillets look good. I have 4 elements on top, 4 on bottom. Everything looks nice and organized. They're all the same size. I really like what I'm looking at there. Same thing over here. We have a fillet density that doesn't want to match up there. It's got 11 to 10. Now, given how many elements there are, I feel pretty good that I can bump that up to 11 or bump the other one down to 10 without drastically changing the element size, given that it's only going to change it by about 10% or so for that given region. So what's nice here is HyperMesh gives you some tools right away to just come in here and just start tweaking with these elements while you're going through it. Now, I would be careful about this little next region up here that we've seen, that kind of this fillet that dips down a little bit. It's like a 3-way fillet. You want to make sure that the elbow, if you would, on the right is identical to the one on the left, or as close to as possible as identical. Or else we're kind of violating that rule here of mesh uniformity, that our features, which are identical, aren't modeled accordingly. So let me show you an example of what that could look like if we screwed that up. Oops, there we go. Perfect. So some of you might be noticing right away, if I zoom in here, we got some triad elements that are starting to form there, and that's certainly not what we're interested in seeing there. But the other kind of thing here that I want us to point out is notice how on the right side, these elements over here, let me select these guys to make them stick out a little bit more. These elements which I'm selecting now, there's first off a lot of them. There's a lot of triads. I don't think that's an aesthetically pleasing looking mesh. But also, if I compare it to the mesh on the left, they look nothing alike. Sure, the regions themselves are the same, but this mesh over here has only a handful of elements. It's got maybe 7 elements in that radial direction, where over here it's got some, maybe 14 as many as. It's just these aren't identical, and that's something we'd really want to avoid because I'd be willing to bet that my stress contours are going to be very different looking now at those two different looking meshes. And why that can be the case simply comes back from what we talked about a little bit yesterday and how HyperMesh is determining element stiffness. It determines element stiffness first from the area or the volume of the element given its shape. Then it applies a material property to that, and that's what's determining stiffness. So the reality is the individual element shape is dependent, for better or worse, on the results you're getting. So you really want to make sure that not only are each of those elements looking the same, but even global features like this entire surface of elements looks the same as its neighbor if that surface is going to repeat itself there. Consistency is key. More than anything, you want to be consistent and as repeatable and as uniform as you can in meshing. It can be a little monotonous in that sense, or it can maybe feel a little monotonous that you're not getting too artistic with it necessarily, but that's really the name of the game here. So how I can kind of clean that up here is what I would do personally is just grab some of these surfaces again. And what I love about HyperMesh is if you want to remesh something, you don't have to delete it. So here I got a surface that I want to go back and remesh. I'm just going to come into my meshing tool, select those surfaces again, and just drop a new mesh on them. And there's some other cool quality of life tools things happening. So for example, we're only seeing the left half of the screen currently be highlighted that neon green, whereas the other elements on the right are still that pink color. So the reason for that is that I'm only meshing the green surfaces on the left here, so we're only seeing those new elements in that neon color. The pink elements are locked in. They're good to go. Those were confirmed from a previous mesh operation. And why I want to call that out is where this green meets pink interface, it's ensuring that it uses the same number of elements on the left side of that shared edge than it is on the right. So I'm seeing I have 1, 2, 3. Let me get that spotlight tool out. I'm using 1, 2, 3, 4, 5, 6, 7 on the right. That same density of 7 elements carried over immediately to the next surface and the new mesh, 1, 2, 3, 4, 5, 6, and 7. It makes sure that it's repeating those densities in the next surface to ensure that your surface meshes are all going to connect together and tie together correctly at the end. So fortunately, you don't have to take too many extra steps to tie things together, but what you really should just be doing is making sure that you have the appropriate sized elements when necessary and that our features are as uniform as possible. And here's an example of that. For whatever reason, HyperMesh wants to place 3 elements on the right side of this edge, but on the left side it wants to go down to 2. I'm just going to make a judgment call and shrink one of those. All of a sudden everything looks to be a little bit more uniform, and it's that much cleaner as a result. So a lot of quick ways to mesh here. Now, the tool itself has some built-in, some checks in there to help you generate a high-quality mesh the first time. You don't always have to go through each and every surface and adjust element edges. It's totally normal, and I would expect you guys to, on some 2/3 or 80%, 90% of surfaces, to not need to worry about the element densities and do those incrementings that I've been showing us through here for a little bit now. And a lot of that comes from just some of the built-in tools with the AutoMesh tool. And I want to point over to slide 14 here for a moment in my chapter 3 slideshow to talk about some of those checks. And there's really kind of a big 4 here that we're going to get familiar with. There are our flow settings, align and size, and the map settings, size and skew. So flow, as it says, is a little bit more concerned with things like our mesh lines and the mesh line flow there. So when we have this mesh flow align setting turned on, it's going to try to do everything it can to give us as quad dominant of a mesh as possible using that mixed mesh type. So that's generally really favorable for us. Off the top of my head, there aren't really too many circumstances I can think of where you wouldn't want that. So I would generally recommend leaving that flow align setting turned on. Likewise, when you turn the size setting on for it, it's going to make an effort to enforce all of your elements are the same size as close as possible. There's some good use cases for turning that on. There's been some situations I've been on when I prefer to have some deviation in size and use trias. So really it's up to you on when to use that. But at this point, I think it's better to use it than it would be worse to not use it, if that makes sense. Now, likewise, there's a couple map controls in here as well. And likewise, those could be a focus on either the size itself or a very important one, that skew setting. What that really helps is prevent a skewing of elements there. So it's kind of funny. That skew one, at first people get kind of mad at it because sometimes it introduces an additional tria, but it introduces an tria to ensure that you have 90-degree quads there. So we're going to play our last game of Pictionary for a moment here together. And I can kind of illustrate that situation. So we're going to draw another terribly drawn surface here. Something like this here, where the bottom edge is much longer than the top edge. Now, if you wanted to introduce exactly 5 elements on top and 5 elements on bottom here, this surface would have to mesh something kind of crazy where it's going to have to do these sort of big line deviations. We'll just do 4 because I already screwed up. Oh, thanks. Four elements, looks beautiful, right? But maybe you don't want to have this kind of this weird skewed angle thrown into your mesh flow there. So sometimes what that skew setting would do is going to ensure that we're going down in a straight line. It just might introduce a tria element along the way, and we'll see where it's going to do that in a moment. It might introduce a tria element up here before it goes back to keeping it straight down. If that kind of makes sense. I know my Pictionaries are very vague there. I hope there's like 2 of you that are thinking this is like the greatest thing ever. I'm hoping that's the case, but I could be very wrong. But where I wanted to go with that is that these 4 controls, align size, and then the map size and skew, are all done with mesh uniformity in mind. And if you're ever in doubt and you're not confident that you're making the right user adjustments on your own, and that's a very normal feeling to have. I'm hoping when we leave this class, we feel good at meshing, but it is something that takes experience to get used to. And there's customers of mine that have been doing this for as long as I've been alive, almost 25 years or so, that are still picking up new tricks along the way. So it's definitely not something that you're going to be an expert at overnight. And knowing that a lot of these controls here are still designed, it gives you that confidence even at a beginner level there. And when in doubt, you know, I feel like you guys can just turn on your mesh tool and I can just come in here and I'm just going to check all 4 of those boxes. And now I'm pretty confident that whatever it's yielding me, if I don't want to make these increment decisions, these 4 in parallel are making those tough choices for you. Now, as you get more experience and get a little bit more picky and have a little bit more specialized requirements for what you want out of your meshes, that's when you can start turning those off again and reintroduce some more manual effort there. But what I love about this is kind of in HyperMesh's and Altair's really bigger software philosophy of we're going to give you the tools you need to be as specialized and specific to your work as possible, while still offering you a practical set of best practices or automated tools in there to save you some of that engineering judgment if you're not sure where to go there. So it's almost like a little bit of best of both worlds there. You can be as manual as you need to, or if you want to rely on the auto tools and the best practices built into it, those are done with some good things in mind. Now, before we shift gears here a little bit and start talking about repairing a mesh and how do I assess my mesh quality, I want to talk to us a little bit about this idea of this tool here, this linked opposite edges with AR, and what this does and why that's helpful. So what I'm going to do for a moment, and we'll see how to do this together in a second here, is I'm just going to delete my existing mesh. And I want to talk about meshing this fillet here. There's going to be 2 things I want to do here.
Garrett, I mean, since you just said the word delete your existing mesh, one question came up: how to retrieve a previous mesh that you might have on. And I know those are depending on a couple of situations. You know, in the case what you just did here, you can undo the delete, use Control Z a few times and get back to that point. But when you're actually meshing and how you remesh something, how can you get I believe that's the question he's asking.
So if you're remeshing and then you've, so let's say you have one surface mesh here. So I'm just going to mesh half my part. And I've been working on this for a day or so, and I come back in here and maybe I accidentally, mesh over some surfaces without even realizing I changed it. And I'm going to just bump up the element size to make it drastically different. And maybe you don't realize you had done that, after a couple operations. So I do some other stuff. It's looking great. And why I bring this up is now you've gotten to a point where it's not as trivial to just Control-Z undo there. So the short answer is, unfortunately, there's nothing inherently that's going to know that that was the mesh you wanted to save, and it isn't readily available to be restored there. Now, Control-Z can help you quite a bit there to get back to that. But another thing that might be able to help out is if you come up to the very top of your software, and I go under my edit here, my little edit menu, there is a command file that's being written out of all of your different commands. So maybe not for a meshing operation, but for some very technical, like a 12-step workflow that you accidentally screwed up and needed to get back to, you can always steal those commands that the button clicks and the mouse controls that you're using are actually calling in the background, and just repeat those button clicks and workflows for you by simply copying and pasting some of these steps. So let me come up here. I'm just going to take a handful of these. You can just take whatever the step would be, and this takes a little bit of experience to know what the commands are for each step. But hiding in your software, if you go to View, there is a command window that I could then just copy and paste those steps into and let it start remeshing those steps there. So maybe not for a meshing or operation specifically would that make the most sense. But a couple of the other splitting workflows, or especially geometry-related workflows, that could be a big time saver there if you accidentally screwed something up and wanted to go back to it. Now, another way you could help, though, control your elements and make sure you don't lose a mesh like that, one thing that I like to do is be very picky and take the time to control where my elements are being placed. Not where they're being meshed on the part itself, but from an organizational standpoint. How is HyperMesh saving my mesh, and where are my elements within the browser view itself there? So it looks like HyperMesh got mad at me right there, so I'm going to launch another session of it here while I let it command.
I think, but in the case, just the Control-Z, going back a few operations, I think that's the use case he's looking at, is where he or she went a few steps beyond, but not too far beyond.
Mm-hmm. I see.
Like you mentioned, like you did it the day before or something like that, and did 50,000 other steps in between. I think that covers what I just wanted to make sure what other options were available besides the Control-Z option, and I think that will help them out greatly.
Definitely. Now, before we kind of get into element assessment, there's one final mesh tool I wanted to talk about here, and this is this idea of the link opposite edges with AR flag. So what the heck is this thing here? So you might have noticed underneath those 4 flow and map toggles we just talked a little bit about, there is one final checkbox, link opposite edges with AR, and it's usually set to auto, and you can just turn that on and off. When this is turned on, this will do you a big favor, and HyperMesh will do its best to make sure all edges that correspond to one another have the same element densities. So by default, we've seen with this turned off, if I take those inner and outer radiuses, like this surface over here, if I mesh it with 2.5 millimeters, it wants to do 8 on the inner radius and 12 on the outer. Those edges appear to be almost the same thing. They're partner edges of an inner and an outer radius of a surface fillet. And we know from our discussion and seeing this today that it could really make our lives easier if those are the same node density up front there. So rather than always having to come in here and, change the inner edge up a couple times and bump the outer edge down a couple times to get me that perfectly orthogonal quad mesh, link opposite edges with AR will tell HyperMesh to detect anytime those edges appear across from one another on a surface and make sure that they have the same element density. So now that I have link with AR turned on, you're going to see here that it's going to automatically mesh it with those node densities fixed for you. So there's some cool things with that here. So we're going to learn another trick and then combine it with that AR trick we just learned to make meshing a lot of our surfaces really easy here. So I'm going to come back to my back side of the part here for a moment. And some of you have probably noticed here that HyperMesh could be a lot quicker to use if you had less surfaces. So as you start breaking things up into more but smaller and smaller surfaces, that's more individual surfaces I have to go through and mesh on my own. So it might be easier to take something like this region here. If I zoom in, I have two surface fillets here, left and right. What if I just got rid of that dividing line between them so this was just one bigger surface? And that's a very popular thing to do here. And we can do so under our geometry editing tools here. And what I want us to start thinking about while we're going through this here is this idea that meshing is actually the easiest part. Clicking a surface, dropping elements on it, that is probably the easiest part to do. And it's kind of funky. I think yesterday, I'm sure I said it, and I'm sure you've heard it from other engineers in the past that, meshing is a skill. It requires a lot of expertise, but once you know what you're doing, that's the easiest part. What really is going to be maybe the trickier part or be a little bit more involved is the preparation leading up to your mesh with your surfaces and your geometry. An example of this geometry preparation could be what we saw yesterday of extracting that mid-surface out from a thin solid or a plated solid in order to use these shell elements with. What I'm going to do here is not extract a mid-surface. We've already seen that this is already infinitely thin. I'm going to start turning off surface lines or merging multiple surfaces in order to reduce the total surface count. I'm not deleting surfaces. I'm not removing area from the part geometry file. I'm simply going from 100 surfaces that combine to be 100 millimeters cubed to being 50 surfaces that still combine to be that same millimeter squared area. So what I'm going to do here is I'm going to take my spotlight tool and I'm going to go back to that geometry tool, and we're going to go to this little top corner menu, the quick edit tool. For you keyboard specialists, I'll put this in the chat again. The F11 shortcut key takes us to quick edit, and F12 takes us to auto mesh. That's a very convenient pairing. Oh, let me put it to everyone, not just Darius here. So F11 is a shortcut for quick edit. F12 is a shortcut for auto mesh. Once you kind of get comfortable with that, you don't ever have to use your mouse to hit return, go to the 2D, go to the auto mesh. That's a lot of clicking. You're gonna feel that in your wrist after a couple hours. What you can, what's really nice here is you can just bounce back and forth on your keyboard, F11 and F12, to cycle between those menus. And we're going to learn a practical reason to do so. Now, in your Chapter 2 slideshow, Chapter 2 Geometry, so if I come into my copy of the student folders here, you had a student PDF folder we talked about. In that, there's a Chapter 2 Geometry slideshow. And this was that big 100-some slideshow I talked about yesterday that you might want to take, the half hour or so to thumb through when you have the time. If I come down to a particular slide in this Chapter 2 slideshow, it begins on slide 20. They have a little bit of a blurb on all of the different options within the quick edit menu. So if there's a particular tool in there and you're not sure what it does, slides 20 and 21 offer a little bit of insight to each of those tools, or maybe even a little bit quicker when you're in any tool within HyperMesh. This is awesome. So right now I'm in that quick edit menu. I'm seeing all of these different panels staring at me. I have no idea what any of them do. If you hit F1 on your keyboard, it'll launch the HyperWorks help. And more important than that, it's context-sensitive help. So what I mean by that is I didn't even have to search in the help menu for the quick edit page. We're going to see right away that HyperMesh, not only did it launch the help, but it launched the help open to the quick edit page for me. So as long as you're using the tool and you're in that tool, so when you hit help, HyperMesh will automatically take you to that particular page for the help menu. The idea there is to really reduce the amount of time you're thumbing through the help page, feeling like you're not doing things correct or really getting bad vibes built up in your head there. We want things to be quick and accessible. And really, when in doubt or if you have a quick question about a tool, it's always that one F1 key away from getting some simple answers for what's going on in the tool there. Now, I'm going to come back to my session here. And I want us to come down into our...
Garrett, can I interrupt one thing since you're talking about help? In your slideshow, isn't there a slide that shows all the shortcut keys?
Yep. Let me get back to that guy here.
Because again, that's extremely handy, is knowing what they all are. Of course, you can type in the online help and have it find you that page. But when you're in your PowerPoint, yeah, if it has that slide too.
So the tool that I really, within this quick edit menu, that I want us to get familiar with is going to be on the left side of the tool. So in my mind, there's two columns. There's a left and a right, pretty straightforward. The tools on the left are concerned with surfaces. The tools on the right are concerned with vertices or points where those surfaces meet, or excuse me, where those surface edges meet. So on the left, it's a lot of surfaces and their edges. On the right, it's the edges and their points. So it's kind of just a different in dimensions there. For now, we're going to focus on the left half, these surfaces and edges tools. And the big one we're going to want to get familiar with today is that towards the middle, it's a tool called Toggle Edge. And Toggle Edge is a multi-purpose, very powerful tool that we're going to get familiar with. And we're going to see how this can make meshing a lot easier. Now, what Toggle Edge allows me to do is, first off, in order to use it, I'm going to left-click the Toggle Edge panel. You're going to notice that only one of these yellow panels can be active at a time. That's to sort of save you from yourself and get confused on where input's going. So we're going to just use the Toggle Edge panel first, so I've left-clicked to activate that. I'm going to leave the tolerance for now to the default value on my machine of 0.1. Yours could be smaller. That's all right for now if you want to bump that up to 0.1. That shouldn't be too big of a problem. Now, how this tool works. Toggle Edge does a couple different things. Left click and right click have different features. There are different functions. So left click, it will cycle through in a kind of a clockwise direction. We'll see what I mean by cycle through in a second here. And the right click will cycle through backwards or counterclockwise. What this tool allows us to do, it adjusts the definition of an edge, and it specifically adjusts the definition of an edge and how it describes the connection between two surfaces. So if you had thumbed through your Chapter 2 geometry slides yesterday and skipped over it intentionally, there's this idea of edge or 2D topology, which is a really fancy way of describing on your CAD file how surfaces are connected at edges. And this might seem really obvious, because I'm sure most of you are thinking, well, yeah, surfaces meet at edges. That's how we know where surface A starts and surface B ends, and we know that they're shared. That edge belongs to both of those surfaces. And that's what we hope to be the situation most of the time. Now, the nice thing is 99% of the time, your surfaces are going to be connected correctly. The edge will be connected to the surface correctly. You're not going to have many problems there. And I think sometimes people think of topology as this like bad thing that they have to repair or can be broken, and then their model isn't connected. At this point, the CAD packages are so mature that's really not a virtual possibility or concern that I would see too much. But what I do want to introduce us to is how topology can be used to make meshing easier if we kind of finagle it the right way there. So what we're concerned with more than anything with Toggle Edge is the definition of edges, and really the only way an edge definition varies is whether or not it's connecting surfaces or if it's connecting multiple surfaces. So what are our types of edges? What are the edge definitions we have here? We're going to see together in a slideshow in a moment that we have shared edges. This is good. It means surfaces are connected, they share an edge, right? That makes kind of sense to us. If two surfaces need to connect together, they're going to connect at an edge or along an edge. There's also free edges. I don't want us to think free edges are always bad, or frankly, I'm going to get rid of the good definition up here because that isn't necessarily always the case. But free edges, we're going to see in a moment, means isn't connected to another along this edge. Edge is floating. So it's almost like a boundary where there's no more material at a surface if you have a free edge located there. And then we're also going to learn that there's something we call a non-manifold edge. We're going to ignore that for now. It's just a fancy shared edge of 3 or more surfaces. And then the most important one, though, for meshing purposes, is the ignored or the suppressed edge. We're going to ignore it for meshing, but not delete it there. So to recap for a moment here, while we're meshing, since we're meshing everything in terms of those nodal densities and letting HyperMesh fill things in, we're already concerned with element edges and surface edges. We also saw in an example where if I have a surface already meshed, it'll maintain that same element density when I begin to mesh the next surface here. So the right edge had 7 elements. It's going to make sure it does it with 7 this time. Even if I went back and meshed that surface the first time with, I don't know, something ridiculous like 20, it'll still make sure it's using 21 elements along that edge the next time to make sure it's connecting together correctly. That behavior of meshing it this way is directly downstream of the topology definition of that edge. And that edge is defined as a shared edge, because those surfaces are connected together. So really, what I'm going to do here is I'm going to pull up our 2D meshing PowerPoint slide together, and I want us to think of this idea in the very beginning, and I want us to look at this little example together, actually. So I've shown this slide before here, but this is a really good way to illustrate the meshing effects of different surface topology definitions. So what we're seeing on the left-hand side of the screen here, this free edge, this is a situation where these two surfaces do not know they're connected together. The free edges are going to be displayed in HyperMesh when you're reviewing topology as a red edge. And free edges only belong to one surface. They indicate that that surface it belongs to is not connected to another surface. So what's happening here is I have 2 regions. I have a top surface. Let me get my highlighter up. I have a top surface in here that I can highlight in, and I have the bottom surface underneath it that I'll spin my spotlight around in. Those 2 surfaces do not know they're connected together because there's a free edge between them. This little dissecting diagonal line, since it's listed as red or a free edge, those 2 surfaces don't know they're going to be meshed together, and as a result, they're going to be meshed independently. And what happens is, if you kind of zoom in on the slide below it, it's going to mesh those. They might even look the same, but they're not truly connected. It's almost like the equivalent of holding just 2 pieces of paper up to one another without ever actually stapling it together. What we would hope to see in that situation is the green or the shared edge between those surfaces. So we're going to see here the arrow is calling out that green surface, or that green edge rather. And what that indicates is that the top surface that I'll highlight in again knows now it's connected to the bottom surface with the highlighted X through it, and they connect together along that green edge. As a result of that, when they get meshed, those individual surface meshes will be tied together appropriately, just like we were seeing in the meshing tool. So I mentioned earlier, topology can make your life easier when you're meshing, and it doesn't come from these connections. These are good quality things to know to make sure nothing is being broken in your mesh. But how topology makes things easier is another edge density, and edge definition, and that's this suppressed edge I mentioned. So what the suppressed edge definition allows us to do, and let me erase those drawings again. Before we had that line cutting right through these surfaces, that square region, and that broke it up into 2 different surfaces. Well, we can actually ignore that edge and just have HyperMesh meshed over it. And as a result, instead of trying to mesh this as this crazy, if I go back to the previous slide, as this weird region with a tria transition on both the left and the right side of it, like we saw in this example, what HyperMesh will do is if you ignore that edge, we'll simply mesh it as a very clean 5x5 region. So sometimes turning edges off can make surfaces easier to mesh. And if I come down to slide 8, this is one of my favorite slides in this entire training. It really illustrates this point that topology can affect our mesh for better or worse, but knowing that, there are ways that we can influence or adjust the topology to make a higher quality mesh. So let's walk through a couple examples here together very quickly. We'll see this in action at the fillets, and we'll take a quick break before we shift gears into 3D meshing here. So just a couple more minutes here, folks. I appreciate the patience. Now, in our first example here, like we're going to see together in a moment, suppressing or turning edges off or ignoring those edges can make your life very easy, or can make it easier for certain regions. So in this first example, we have again, a square region with this kind of radial edge going through it. HyperMesh, since it does everything edges in, will force nodes to exist along that edge, and you're not really getting a clean mesh flow here. This is a really kind of ugly mesh. There's a lot of funky things going on where I have small elements, I have skewed elements, I have 5 elements meeting at this weird node in the corner. There's just a lot of inconsistent things happening here. I think we'd all agree that if you ignore that edge or suppress it, it's going to give you a lot easier and cleaner mesh at the bottom there. Likewise, though, it's not always just remove edges. Sometimes splitting up bigger surfaces into smaller and smaller surfaces can be more helpful. So what I like about this next example, we got the plate with the hole in it. The first mesh that came out of there isn't perfect. It's not that bad. But one thing I don't like about this mesh here, if I bring my spotlight tool over, is I have a clear 2 rows of elements above the hole, but below it, it goes from 2 elements to 1 big element back to 2. It's not really inconsistent how it's handling the regions outside of that hole. What this user had done was, we're going to see how we can do this together in a moment, they actually split this region up into quadrants, and by meshing those 4 surfaces individually, well, they got a much cleaner and certainly more uniform mesh on the bottom mesh there. And likewise, sometimes just removing the corners or adding in fixed points, which enforces a node to appear at those locations, can help, or even merging vertices. So this is an example where there's 2 independent lines that are forcing a small element to exist. Sometimes smushing those together can really yield us a higher quality mesh there. So if there's one thing you take from today, it's that we can manipulate our surface topology to give us the cleanest mesh possible. And we're going to learn how we can do that together in a very simple way, looking at this little heat shield parts fillets. So let me back out here for a moment. I want to mesh this top fillet first, like I said before. I like to do maybe 5, 6, 7 surfaces at a time when I'm meshing. So I want to mesh all of these surfaces selected here. But I also know that this bisecting line right here is kind of screwing things up. So what I'm going to do is I'm going to come in my quick edit tool. That's the geometry menu. And in the top right corner of the panel area, quick edits right there. And I'm going to select my toggle edge tool. Now I mentioned before, toggle edge, if you left click, will cycle through different edge definitions in one direction. And if you right click, we'll go backwards. And we learned there's a couple different edge definitions here. We have shared edges, freed edges, and suppressed edges. I'm going to ignore these guys for now. So really what happens is you can almost kind of draw like a wheel here, where I have a shared edge, which can go into a suppressed edge, or it could be released into a free edge. Oh goodness, my mouse handwriting is horrible. But what I wanted to show here, and it's much easier for me to do this on a whiteboard, is I'm starting with a shared edge definition. If I left click I can turn that shared edge into a suppressed edge. Whereas if I right-click, I will turn and release that shared edge into its individual free edges. So let's come back here for a moment. Toggle edge lets me take any green edge, and if I left-click it, we'll simply ignore that edge. It's no longer there. If I right-click a green edge, it'll release it into two separate free edges. I know it only looks like one red edge here, but if you zoomed in infinitely small, or I guess as far as you could go, I'm going to really try to break my graphics. We're seeing that this is an infinitely small gap that exists between those surfaces, because remember, a red edge is a free edge that belongs to only one surface and one surface only. Those free edges let us know that those surfaces are not connected. So there might be some situations when you'd want to release that connection and free up the edges. Now, likewise, I said this was a cycle though. So just like I have a free edge, I could left click to go back to a shared edge. So what I'm going to do is I'm going to select one of those free edges with a left click. And what it had done was it detected that there was another free edge, another red edge within this tolerance. That's why there's a tolerance tied to the tool. And it's essentially a gap. What I've said here is I've set this to 0.1. And when I went back here, let me undo this. I'm going to click one of these edges. What HyperMesh is going to do, it's going to take the edge I've inputted, build a cylinder around it, and that cylinder is going to have a radius equal to this tolerance. If any other free edge falls within that tolerance value or that cylinder, it'll smush them together and treat them again as a shared edge. And then like we saw, once you have a shared edge, if you left click it one more time, it'll turn it off. In general, you should really only be using toggled edge. It is most commonly used to suppress and reintroduce the shared edges. So you often are going to bounce between the dash blue suppressed and the green shared edge there. So ultimately, why I'm concerned with this, if I zoom back out, I'm going to suppress that edge going through the middle of that fillet surface and maybe the one underneath it. So now when I go back to my meshing tool, that's only going to be considered three surfaces. We'll see that the mesh line's going right through that blue dashed line there. It's got no regard for it, and it made my life a lot easier. Now, if I come over all the way to the positive X side of the part, looking at this flange over here, let me zoom in a bit. There's a lot of edges with this part here. If I even zoom in more, just this one fillet region over here, it's got all these different edges. I could come back into my quick edit tool, and I could start turning off a handful of these. Now, you don't want to turn off every edge, or else if you lose, all of your edge definition in the model and you have no way of guaranteeing, where one surface meets another, you start to lose those definitions. But I can come in here and just manually turn off a lot of this stuff to really, simplify this part here and make the meshing duties that much easier. Now, what's really cool about this, to go full circle, like we saw in the slideshow, sometimes more than just turning off edges though, sometimes adding your own edges is necessary. And what's cool about that is not only does this quick edit menu have that same toggle edge tool I've been using to turn everything off, so toggle edge is the old suppress the edge tool. At the very top of this column I mentioned, we have some split tools. We have split surface to node and split surfaces by lines. So if you do the node to node option on that top left corner, I can just start picking corners of these edges to introduce an entirely new surface line on my own. Or likewise, I could take the node to line tool and pick a node, pick a line, and HyperMesh will split that according to the line's normal direction as it intersects with the selected node. So there's some tools in here immediately that allow me to split up these surfaces in my own definition, as well as a toggle edge tool that allows me to come in here and turn some of these edges off. And I think you'll agree that if you come in here and you suppress a handful of these edges that you don't need, that weren't adding to the part definition, it's going to make things a heck of a lot cleaner to come mesh, and that's ultimately a good thing for us. Anything that saves you, the user, a little bit of a headache, I'm all for it there. So I think we could agree that, with all these blue lines turned off in here, a lot easier to mesh. And now what I can do with this, I'm going to come in here. I can just select these new, bigger surfaces. There's going to be less of them, though. And maybe this is something that's going to be a little bit easier for me to mesh now. because there's less surfaces for me to worry about while I'm going through it. So really powerful stuff there. And like I said before, not only can turning off those edges kind of make your life easier, if I come back to that AutoMesh tool and we've started all of this off here, we're not going to forget about our little link opposite edges with AR tool. So now I got that turned on, and look at that. In just a couple of clicks now, I'm able to get perfectly even meshes at my surfaces. And the real reason why was because I took the few minutes to clean up my topology beforehand. Now, the final thing I'll say about this is it's good practice, and I would recommend you sandbox around with this exercise if you have the time, if you're really interested in getting, some quality experience in 2D surface meshing. But you're not wrong if you're thinking about this and saying, there's got to be a better way for me to be able to clean up my topology or these extra surface lines than me just manually going through one by one and having to turn on or turn off certain edges. And that's totally true. I would recommend getting familiar with that workflow and experimenting with it to know how to do it when you need to. What I'm going to do next here is I'm going to come into auto cleanup. Not auto cleanup. I'm going to go to my geometry menu. And just under that quick edit tool, if I come down a few tools, there's an auto cleanup tool. This auto cleanup tool will allow you to take all of those surfaces. So I can do that Windows selection we learned yesterday, hold shift, grabbed all the surfaces. And then what I can do here is I can come into edit parameters and edit criteria and start specifying how I want my mesh to look. So the parameter file takes a little bit of tuning, but this allows me to come up to a basics option and say, you know what, I want to mesh this with 5mm elements or whatever it's going to be. So I need you to turn things off knowing I want to mesh with 5mm elements. And likewise, I can come into the criteria file. You can leave it to its default. You can adjust it yourself if you have a specific element criteria. But I can come in here and again, just give it a target element size. Do whatever I need to do. And then I can come in here and hit auto cleanup. Once I've adjusted these these couple target sizes. And what auto cleanup is going to do is, knowing the element size that I'm trying to mesh with that I've specified in the cleanup tool, HyperMesh is actually going through this part and automatically turning off edges for me. So let me hide the mesh for a moment here. HyperMesh turned off all sorts of edges for me, not on just the right side, but the back side of the part as well. We're going to see all these edges turned off that I didn't want to work with. HyperMesh decided for itself to turn those off using the auto cleanup feature. And now when I go to mesh this, might be a little bit easier to work with there. So there's certainly some automated tools in there that can help manage those different edges. So before we take a break here, I'm seeing a question that came in a few moments ago from Cedar. Will it make sense to remove all the edges for a smooth mesh? No, that's something you'd actually want to stay away from, Cedar. And the reason why is, let's look at that together here. So if you turned off all of your edges, like I've done here, so the only edges I've kept on my part are the exterior boundaries of the part here. That's a dangerous thing to get into, because now I've lost definition on where this fillet starts and where it stops. Where is it curved? Where is it planar? Because now if I come in here and I just mesh these new surfaces as one big smooth surface, like you're saying, yes, it's smooth, but where does a fillet start? Where does a fillet stop? Look how much definition we've lost on this mesh. That's something we really want to stay away from. So definitely problem. There's benefits to having them. We want to try to find that sweet spot of what are unnecessary feature lines or surfaces that I don't need to ensure I have elements or nodes at. Because the biggest thing to remember is that those surface lines are giving a kind of a guide or a skeleton for the mesh to ensure that it's always going to have nodes at those edges at. So you don't want to just turn off every edge. They sort of serve as a guide there. We just want to be smart about turning off some of the edges when we have too many in place there.
And you also see, Garrett, that for the same thing is the mesh quality is really poor. You have Jacobian issues, you have Warpus issues, so it's too free form. And as you said, you need those edges to define more accurately the geometry you have.
Yeah, and then before we take a quick break here,
there's that second question in there from Rahul about the ratio, and I don't know if it's in their documentation, the ratio, but I know it's in our FEA practical aspects guide, though.
Yeah, 10% is the rule of thumb that I've been taught to. That's a good one for a ratio of trias to quads, and if it's even 15 or 20, Raul, I don't want you to think like, oh shit, I have 20% instead of 10%. It's not as obvious to just have a number listed there. The most important thing you'd want to keep in mind, and I know this is a vague answer, and I don't mean to be, but this is truly more important than any just golden ratio to always remember, is to always just keep making sure you're thinking of these things in terms of element uniformity. And I'm trying to find where I had written that bad boy down. And more than anything, more than just having, I have too many trias or I don't have enough trias, if that's even a concern of ours. More than anything, you just want to make sure that your smallest element isn't substantially smaller than the average size, or vice versa, that your largest element isn't substantially larger, like we're talking, 50%, 100% bigger than the average size. Or the other half we kind of talked about, that I have a fillet modeled with 2 elements, but then I have another fillet of that same size modeled with 10 elements. You're not really modeling those features the same way. More than any ratio of quad to tria, those are going to have bigger effects on your results than anything, because even though the math might be 1% off as you had a perfect ratio of trias to quads, if you don't feel confident that you can make the correct assessments and comparing those results on the contour because they were modeled so differently, it doesn't matter how accurate the result was anymore, because you can't interpret it correctly anymore. And that's something we want to avoid. And I think that judgment call will make a little bit more sense once we get into our last lesson of post-processing. I found from my own life classes that once you start seeing these stress results and seeing how stresses form on individual elements, that's going to start making a little bit more sense and helping build up your intuition on what's going to be a quality surface mesh. But if you had to have a blanket answer, though, 10% is a good thing to shoot for. But I also don't want you to take that and be nervous or worried if you have 12% trias or even 15% trias in there. There might be some reasons based on the shape of the surfaces that's forming. And like we saw, those could be a necessary evil. So what I'm going to do here is I'm going to give you guys just a 5-minute little break here before we kind of shift gears into the 3D world to end today. Actually, before we even get into the 3D world, we got a couple things I want to cover. I want to talk a few moments on the mathematical assessments of element quality. We've talked about this eye test and making sure they look similar, but we're going to learn some more numerical ways that we can assess a mesh. And then we're going to talk briefly about some of the ways we could do 3D meshing for our volume parts. And that's going to put us in a really good spot to kind of wrap up before we get into our final lesson later this week here. So I'm going to give you guys 5 minutes if you need it to get yourself a cup of coffee, stretch your legs for a moment. What I want to do, though, in these 5 minutes here is I got a question. Someone had asked me to go back through that auto cleanup tool. I'm happy to walk through that here before we kind of pick up and shift gears here. No.
Okay, I thought you also needed a bio break, but okay.
No, very quickly here. Our auto cleanup tool is hiding in the that same geometry menu as our quick edit tool. And you're going to see here, there's a couple other edit tools you're welcome to get familiar with and experiment with. There's a whole edge editing tool, which is a little bit more robust tool set of that toggle edge tool we're getting a little more familiar with. And there's a point edit tool, which I personally stay away from, but there's a lot of fancy things you can do with that. But more than anything, we have this auto cleanup tool here. And auto cleanup is driven from 2 halves. It's driven by a preference file, which is geometry specific, and it's driven by a criteria file, which is element specific. And what it does is takes these 2 files, which are sort of like instructions, and does toggle edge operations for us with these instructions in mind. So those are the 2 files that are driving an auto cleanup procedure here. We have a preference file and a criteria file. The preference file, like I said, is geometry specific. So this is going to be things like defeature or remove any fillet with a radius, less than 5 millimeters, or defeature any hole with a radius less than 10 millimeters. That's the kind of things you can specify in a preference file. Is how are we managing features on the part, and what do you want HyperMesh to get rid of automatically? What do you want it to keep in there? So you can get very technical, and I've seen some of my automotive customers do this quite a bit, where OEM companies will just have a big master preference file where they'll say, hey, anytime we find a fillet between 0 and 5 millimeters, get rid of it. 5 to 10 millimeters, ensure exactly 3 elements of the radial direction. 10 to 15, ensure exactly 5 elements of the radial direction. Like they are pre-meshing their parts essentially using these preference files. Whereas the criteria file, and I think this is what some of you that have maybe already been exposed to FEA a little bit are kind of geared to thinking, this is more of a strict element quality definition. So what this criteria file says is it just establishes the failure thresholds for certain element quality checks. And we're going to learn about those in a moment here together, but the different quality checks that you could have are, element size. So there's a failure for too big of elements, too small of elements. Element shape, there's failures for not square enough, it's skewed, whatever it could be. Or really a handful of those. There's all sorts of different ways you could describe how perfect or not perfect the geometry of a particular square is. And that's what our criteria files are typically concerned with. So for now, I would use a lot of the software defaults, but the only 2 things I would adjust the average element size parameter or option in each of the files and go from there. And certainly as you get more familiar and confident with the software, that's where you can add more of those different options. But what I mean by that is I'm going to come into my auto cleanup tool, and here I'm going to call out that it's already got listed here a target element size, and I have the option to edit my parameter and edit my criteria file. What I'm going to do is edit parameter, and I'm going to go up to basic parameters, and I'm going to set the target element size to whatever my target is. For this time, I'll adjust it to we'll do 5 this time around. Then what I'm going to do is I'm going to come into the criteria file, and I'm going to do that same thing. At the top, I'm going to change the average size to be 5. Now here it's giving me an error that there's something going on with the 2D maximum row, so I can see right away that I just need to set a new failure limit for a maximum size, and maybe I'll just make that 7.5 or 8. And so the reason that specifically erred there was it wouldn't make sense to say, hey, HyperMesh, try to mesh everything with 5 millimeter elements, but also consider anything at 5 millimeter element too big of an element. It can't be both the target size and the failing criteria. So we had to make sure that the failure limit was a little bit bigger than the average element size in this case. That's why I had adjusted that. But going back to the question of what I'm doing with these auto cleanup tools is that right away, just make sure HyperMesh knows the average element size you're working with. And internally, it's going to build the thresholds with some percentages around that average size there with some best practices. So once you kind of just specify those thresholds, the next step is to just run the auto cleanup tool. And this is going to be turning things off for you as you need it there. Now, some questions.
There's the same. There's one more question that just came in. If you want to take a look at it, but I'm not sure if you want to first jump back onto the next chapter you're going to go to.
No, this is good. This is because this kind of leads into what we're going to go in with the 3D2 here. So the first of the questions coming in is how much of a difference does it make using only the auto mesh option without refining the mesh? In general, I wouldn't be worried about that. about not refining or preparing the geometry. I don't want you to think that if you don't do that, you're totally SOL and that someone's going to come out and, from the room and slap you on the wrist and say, hey, you're screwing up. You didn't refine the geometry. Refining the geometry is, in my mind, a very practical step to make things easier, but not always necessary. And it might not always make things easier. It's really dependent on what that geometry is. So unfortunately, that's a really big can of worms. There's a lot more things it's dependent on, and it would have to be a more case-by-case instance. But it's okay if you don't want to refine the geometry. And one of the specific things I can say that's nice about working with students is that your design teams tend to be a little bit smaller. And I'd love to be wrong there. Certainly feel free to chime in and correct me if I'm wrong. But you guys have a little bit more working and closer relationships between the folks doing the CAE work and the meshing and the designers who are doing the more CAD drawings and getting those geometry files prepared. So knowing you guys have those good working relationships, or maybe it's the same people doing both, it's a lot easier to give yourself high quality CAD to mesh moving forward. For some of our customers in the commercial industry, it might be a completely different group of people who are doing the CAD design and who's doing the meshing. And because there's that much disconnect, the designers, or excuse me, the CAE guys might not want to go back to the CAD guys to have them refine the geometry. It might just be easier for them to avoid the emails or the phone call game just to do it themselves there. So that's another thing I can say about it as well. The fact that you guys are drawing up your CAD, if you find yourselves having way too many surface lines that's making meshing hard, well, the easiest answer at that point is kind of frankly just go back into your CATIA file or your SolidWorks drawing file and just adjust the surface definition within the CAD tool itself there. And that's one of the luxuries that I think you guys have as well there. And then the final kind of follow-up we got to that question is, how influential is refining on the results themselves? Maybe back in the day, certainly, but from the refinings that we've seen here, it's more of just trying to make sure elements are as high quality as possible. And that's something I want to hold off to our final day together. Again, once we're seeing these mesh results together, I think there's going to be a light bulb moment for a lot of us once we see a stress contour. Because the reality is, OptiStruct, our implicit solver or whatever solver you're using, knows how to account for the fact that a perfect square is one thing to do math on. That's as close to a perfect square as I'm going to draw. You're going to have to deal with it. And sure, I don't want to say that HyperMesh wouldn't know how to do math on a diamond or something more skewed if I draw many, many different squares. Inherently, at this point in time, with 2020 software, HyperMesh and OptiStruct are smart enough to know to do slightly different math on all of these slightly different shapes and can account for the individual element deformation. So the reality is the solvers are so good that individual element quality isn't as maybe important as it was once upon a time. And Darius certainly, tell me I'm wrong if I'm wrong in that case. But more than anything, you want to make sure that you're being consistent. And that's the biggest thing. FEA solvers have so many logic checks and best practices built into them. It's kind of hard not to be accurate with an FEA tool for a lot of structural and static purposes at this point. But more than anything, you want to make sure that when you're looking at that result, because of things like not using a uniform element size, or because you're doing different meshing strategies at different parts, what you want to make sure is that when you're looking at a high stress region, you should feel good that not only is a high stress region, but the thing I'd be most concerned with is how much high stress is that relative to another section on the part. And more so than any individual element quality, which we're going to get into next, it's that consistency throughout the part that's probably the most important thing for any given mesh there. Consistency is what's going to give you accuracy. The tool on its own is pretty accurate at this point. And there's not a lot. You'd have to really go out of your way to screw up a mesh or something like that to have an inaccurate result. It's consistency that you're really looking for there.
Yeah, I'll just add to it, it's just the element qualities. It goes with your consistency, those. You want to make sure your warp bridge and Jacobians and all those things are in line to the standards that are needed for it. So if you're going to have pretty warped and bad elements, then that'll quickly cause problems.
Perfect. Well, thanks for that, Darius. So what I kind of want to move into next here is talking a little bit of how do I actually know mathematically if I have a high quality element? What does a low quality element look like? What are these things that I actually want to be keeping an eye out for so I know if I need to refine my geometry or not? And what I have up here is that same that mid-surface component here that we saw earlier from yesterday. It's that same clip model. We pulled out the mid-surface, and I want to talk about some of the geometric features in here that we might want to clean up to make meshing this a lot easier. And I'm actually going to start from the beginning here. So hopefully you guys remember this little doodad from yesterday. It was the thin, solid bracket. It was about 0.91 inches thick or so. And what we had done from this was we're going to extract the mid-surface out. But we're going to talk about some of the things that, in my mind, are going to be practical to de-feature out or refine with the mesh quality in mind there. So what I'm going to do next here, I'm going to take this part, and I am going to do what we had done yesterday and come into my geometry tool set. I can come to my mid-surfacing tool in that center column, and I'm going to select the solid and extract out that mid-surface. So place the mid-surface in its own component. I'm going to isolate that component in the model browser. I just turned off the flags for the parent geometry, so it's hidden. And to start here, I'm just going to throw on a mesh to begin with. But a couple things I want to call out. We're going to see that we still kept those washer holes in the mid-surface. There's still a few small fillets and jogs. So like there's a small little lip here that got kept in the model. A few little things like that. Now, when I go to mesh this, and I'm going to mesh this with a 5mm mesh to start, there's a couple problems starting to come up. I think we had agreed that this didn't look as good as some of the meshes we saw earlier. And one of the things that I don't like is that I have a relatively boxy surface. And let me just isolate this relatively boxy surface. This surface right here that I've selected is relatively boxy. Sure, it's got a rounded corner. It's got this little key slot in it at the left, but for the most part, it's pretty square. But when I meshed it, for whatever reason, maybe I wanted to include this like radial flow where it's not that boxy. It's got all these wavy lines, and I'm not sure where this like semicircle profile of edges wanted to form. Let me get that spotlight tool. This is the edge line I'm talking about here. I'm not thrilled with why it's got this curved profile going through the mesh. Same thing over here at the top, just not as grid-like as I was expecting. So one of the things I'm going to do is adjust the topology or refine this geometry to help it out a little bit. So what I can do here is one thing I like to do to help me out is I'm going to take my spotlight tool. There's a little setting on this little vertical toolbar just to the left of the graphics area at the bottom. And it's called Show Fixed Points or Display Fixed Points. It doesn't look very influential on the screen there. It just makes your corners of your surface edges a little bit more obvious to identify. And I'm going to come back into that Quick Edit menu as well in here. So I go to Geometry Quick. Some of the things we can do are all built around this Quick Edit tool. So maybe what I'd want to do in this case is simply, we've learned a few of these surface split and toggle edge tools. Well, one of the ones we can learn about here is actually this tool called Replace Point on the right side. And what Replace Point allows me to do is select a point that's going to move, select the point that's going to retain, and if I zoom in here, I want us to watch how the node on the right here is going to get squished to the node on the left, and it's going to kind of de-feature out that key slot a little bit now. And likewise, I don't have tools just to squish points. I can even come in here and add a point. So there's this little add point on a line tool where it'll add as many equidistantly spaced out points, or in this case, one, on any given edge that I select. So I'm going to come into this little curved radius here, and I'm going to add one point in the middle there, just so that way I make sure that there's a node grabbing that exterior corner. And maybe to help clean it up further, the tool just above it is this Add Remove Point tool, where if I left click, I can add points, which will force nodes to exist there. I'm going to undo those. Or I can right click to remove points, to maybe to introduce some nodal requirements. And right away, just by tinkering with that little key slot up here and merging those points and coming down to that radial edge and just adjusting how the points were defining it, I'm getting a little bit more of a clean mesh. Or maybe another thing I could have done, and this is what the exercise step-by-step has you guys go through. I would highly recommend taking a look at the Chapter 3 exercises when you have a moment, is I can use these split tools in the quick edit menu to help me out here. So what I'm going to do is take this little tool, and we're going to get familiar with one today called split surface to line. I could take an existing node or a corner and project that all the way to another edge across from it, and it will split the surface along that. So let me show that again. I'm going to choose the option split surface line. I'm going to select a node. I chose this corner node here, and then I'm going to choose a line, and it's going to draw and split the surfaces about the line normal to the projected line that still intersects through the selected node. So what that allows me to do is really cut off and square off that edge at the end there. Now, if you wanted to, you could keep going through this and really what my old boss used to call Swiss cheesing your model. But by Swiss cheesing your model, if you find that little sweet spot, this makes it very easy now to have one surface turned to 3, and then I could go back and mesh these 3 surfaces and maybe start to getting this look a little bit more uniform and cleaned up there. Let me just see if this will work. Aha! Gives me an excuse to talk about this. Perfect. So one other trick that I can show you guys. Once you're meshing, and I've selected some surfaces here, if you swear that something should be meshing more boxy, is the terminology I like to use, and that it should be a more square mesh than it is, and you're getting a lot of triads when you're convinced it should be an A by B grid mesh, when you're in your interactive method, and it always defaults to that edge density tool we got familiar with that allows me to increment up and down those edge densities, but I can actually change this little radio button to be this mesh style. And what mesh style is, it actually lets us know that HyperMesh is already making a judgment call on every surface and trying to map it as either a circle, square, or triangle. So I'm going to steal a slideshow for a moment. I'm going to scroll down in here, find the correct slide that calls this out. Pardon me. Here's the little guy. So what's cool here is HyperMesh has some built-in meshing strategies or approaches or frankly templates for regions that are shaped as a square, a triangle. Circle is a very practical one, so that way you get a clean, uniform mesh at circular profiles like the end of a cylinder, or even pentagon faces is another less common one. But like this surface here, even though it's not a perfect square, I want it to mesh as if it was. So what I've done here is I've gone from that density tool before I finish the mesh, and I've gone down to mesh style. And you're going to see here that it's at defaulting to toggle surface. What that means is I can just click on the surface to adjust the shape until it gets to the square. Then I'll go ahead and I'll hit mesh. And it should try to mesh it again, this time with that squared surface there. So a really quick little way for us to go through that there, to kind of instruct it to try to mesh something as a surface. Now, some of the other reasons you might want to refine a model, though, could be these holes here. So I'm going to just mesh this surface again with that same 5mm mesh around these bolt holes. But we're going to see here, bolt holes are another feature, sort of like fillets, that can provide some challenges at meshing. And the first reason why is that you have to put elements around a hole, which sort of forces very small elements. And I'm sure as all of us have experimented with, it gets pretty challenging to approximate curved geometry or perfect circle with a limited number of straight lines. So part of that problem is, well, the lowest number you can truly model a hole with is 3 elements all the way around it. And I don't think anyone's too thrilled about trying to model a circular hole with a square or a triangular slot or even a square slot. So a common requirement for bolt holes we wish to keep is to ensure we have at least 6 or maybe as many as 8 elements around that bolt hole. But as we're seeing, and we learned earlier, as you increase the number of elements around a hole, the edge itself and the element itself gets a little bit smaller. And it's very common to consider elements as small as their smallest edge. That's one way you can think of element quality. So I think we'd all agree that this is really ugly looking for now. But what I want to get into before we end today with is actually mathematically proving that my orange elements I've recolored here are truly low quality elements. So to review, so far we know that we have F11 is the keyboard shortcut for my quick edit or my geometry refinement menu. And we're going to remember here we have some cool tools for toggle edges or surface splits and really make meshing easier toolkit. That's what I've always thought of it as. And straightforward enough, F12 is our auto mesh 2D meshing tool there, kind of the bread and butter of HyperMesh. But the newest one we're going to learn here to end the day is the F10 shortcut key going backwards. This is my quality check tool. How good or bad are my elements? And we can determine that using the F10 quality check tool. So I'm going to hit F10 on my keyboard, and we're going to notice that my panel area has been adjusted to now be all these little green tools here. What I want to go off here is it'll default to 2D element quality. If not, we're going to set it to that 2D radio button. And there's all of these different parameters here. There's something calling warpage and aspect for aspect ratio. There's 2 length checks for minimum and maximum size. There's different angle requirements for the internal angles of a quad or a tria element. In short, these are all the different numerical or mathematical terms that can describe if an element is high quality or not. And again, we're going to kind of dumb it down and think of high quality elements are generally those that match their perfect shape. For quads or squares, it's a perfect 90-degree square. For a tria element, it's looking to be a perfectly equilateral 60-degree triangle. Now, how this tool works is you set a threshold, and then you click the green panel to check for only that check. So to start, I want to check the warpage of my quad elements. Warpage is a classification of how not flat is your element. A perfectly flat quad element, it would have 0 warpage. So generally, we see warpage as we use flat elements to model curvature as it gets warped around that curvature. So here, since I've only mapped planar sheets, I shouldn't expect any warpage, though I'm getting an error message that I do have one element 180 degrees warped. And that's because I had to do some inversion stuff around that bolt hole. So that's a big meshing error that it's already calling out. We also have some aspect ratio checks in here. Aspect ratio is really just a measurement of how much variation is there across your edge lengths on a given element. You should typically expect to see, in a perfect world, we'd have aspect ratios of exactly 1, which lets us know all of our edges are the same. But we know that's not always going to be the case because our parts aren't perfectly square, and that's okay. But I don't want to scare people into thinking that, just because you don't have perfect aspect ratios mean your mesh is poor. That might just be that way because that's how the part is designed. It's inherent to the shape of the part that you can't always just map any given arbitrary area with perfect shaped squares and triangles. There's going to have to be a little bit of wiggle room to make that area possible. Now, the first question I can already anticipate coming in here, if I haven't got it already, is, well, what the heck do any of these checks mean? How do I know what the Jacobian is or the chord squish? What is any of this? And you actually know the answer to that already. And that is we are always an F1 key away from launching the help to get our answers. So if you actually launch help from the quality check menu, at the bottom of the help page, if I come down here, or it's no longer at the bottom, excuse me. Oh, they've just moved it. It's all of the actual quality check definition. So here I can see that the warpage calculation is actually describing how out of plane one node is to the other 3 for a given quad element. Side note, one way you can think of that is only quads can warp. Tria elements are always planar because there are only 3 noded. The aspect ratio, like we said, it's the ratio of the longest edge of an element compared to its shortest, and it's even giving us a good rule of thumb for these. And what I've always assumed here is these default values are a great quality requirement, in the sense that if your mesh can meet the default values, that is not just a good mesh, that is a great mesh. Like print it out, hang it up on your mama's fridge kind of great mesh. I don't want to be, please don't quote me verbatim on this, but some general quality guides here, and I'll share this with everyone here, are kind of the following here. I always kind of shoot for a warpage of 10 degrees, an aspect ratio of 10. My minimum edge length should be no more, or should be no smaller than about 20% of my average size is a good rule of thumb. And my maximum element size or edge length should be no bigger than 2 times the average element size. So for me, I'm always thinking of it in terms of I don't want anything to be smaller than 20% of the average size. I don't want anything bigger to be twice as big as the average size. I've seen some people use a requirement of the minimum size should be, the average size over the square root of 2 was the rule of thumb they use. They would divide out by 1.4 and use that as a rule of thumb. And some people would also do, your maximum size is, the average size times the square root of 2. I think that's a really tight window. You're going to have, especially for smaller features, the occasional really small element. So that's where really my 20% or even 10% of an average size, it's okay. Sometimes you need to have the occasional small element in order to capture your geometry. But bigger than that, though, usually 10 degrees is what I'm aiming for a warpage. 10 degrees for an aspect ratio, kind of nice, easy number to remember, as well as the final one in here that I like to look at as well is a Jacobian value. And 0.7 is great. 0.5 is as low as I would go. And what a Jacobian describes, if we come back to our help menu, it's the deviation from an element's current shape compared to the ideal shape there. So anything with a Jacobian value of 1.0 is considered the ideal shape. It's sort of like a grown-up version of the aspect ratio check. And generally 0.7 is considered an acceptable limit. 0.5 is typically the lowest I've seen for people use acceptable limits. And that's kind of how I would consider that. So knowing we kind of have a way to determine, from the help menu, we can figure out what these checks are, and it even had some respected limits in there. How do I practically use that now? So maybe what you've gone through here is you've mid-surfaced the part, you meshed it. I just did it very quickly there. But now you're coming through here. The next step is to come into your quality check tool. So I hit my F10 there, and I'm going to go through these one at a time. So I hit my warpage check. It lets me know I had 0 of 500 elements fail, 0 of my elements failed. So in the bottom corner of my screen here, HyperMesh is communicating to me how many elements met that check. All of them did. There wasn't anything warping. Aspect ratio, I'm getting a notice here that there's a couple elements pushing an aspect ratio of 10. They got a pretty high ratio of 9.89. And the reason for that is these elements are very long than they are wide. And that's because that fillet is very short. So I'm going to come back here. I'm going to use that spotlight tool again. We're going to come over to our geometry menu. And let's take a look at this length check for a moment. If I measure the length of that fillet, I can see here it's not even a millimeter long in that edge length. So if I'm meshing this with 5 millimeter elements, that probably wasn't a fillet I'd want to capture. I'd either have to do one of two things. First, I could either reduce the average element size to be small enough to capture this fillet. We're going to remember earlier we talked about this idea of how do I determine my average element size? Well, I got to figure out, what the smallest feature of interest is. This feature is very small. It's not even I think this model's in inches. It's about not even 3/4 of an inch. And typically we want to mesh things with the smallest feature in mind. So I can either drastically reduce the element size to be order to capture this fillet in a high quality way, or I could decide I don't want to capture the fillet and I'm going to approximate it out as a straight line. And that's where we have a geometry tool just above the mid-surfacing tool, we have a defeature tool that allows me to take these surface fillets here, and I can actually just remove them out from the model there. And you'll see HyperMesh actually went back and automatically meshed the part around those. And sure, I lost some of that curved features there, but maybe in this analysis, I didn't need to see any stresses at those fillets, and I just needed to model this bracket in with some weight. I don't need to see the perfect curves there. And as a result, if I come all the way back to my quality check, well, I don't have failing aspect ratio elements along that interface anymore. So maybe I would do a similar thing to defeature out that fillet, at the other side. And that'd actually be preferable, so that way we're doing this in a uniform way where we're not just removing some fillets and keeping some. We want to be pretty smart about being consistent about removing these fillets there. So I'm actually going to come in this part here. And I've seen this plenty of times. I'm just going to remove a lot of these surface fillets there to make this thing a lot more simple to mesh. We'll leave it at that. Looks good. Nice and boxy, as I like to think of it now. So now that we've defeatured out those fillets, because they were making it challenging to mesh, we had very long and skinny elements because that fillet was so short that it turned out, just getting rid of the fillet. And we decided, for the sake of this example, I didn't need to see those fillet stresses. And certainly if that's the case in your situation, feel free to defeature those things out to make your life easier. But now when I'm getting back to that aspect ratio, we don't have those elements failing it. Instead, I just got a few other ones. So likewise, I got those keyhole slots giving me problems again. So like we had done before, where I'd gone into my F11 quick edit menu, you're going to learn a little trick here. F10, F11, and F12 are all next to one another. You're going to be bouncing between those all the time there. F10, F11, and F12 are like the three musketeers of surface meshing. But now that I'm back in that quick edit menu, I'm going to use that replace point tool again, this guy over here. And replace point is going to allow me to take this node up here with that green edge and smush it all the way over to that node over here. And that's going to get rid of that key slot and clean up this mesh a little bit for me. Sure, we're not being true to the geometry anymore, but we're limited to, at some point we're going to have to make a decision on, do we want to include these features? And if so, are we willing to pay the mesh price and the numerical cost of modeling those features in? Now, I have my HyperMesh set to auto mesh things as I make edits. I'm going to just come over it and remesh it just to clean that up there. And that's fine. I'm really not sure why that thing meshed so poorly. Better. Now, the final one here I want to talk to us about is we saw bolt holes can give us some challenges as well. So the same way in that same defeature menu had a remove fillet tool. So again, that geometry menu, we had the defeature tool in the middle column. Yes, we can remove surface fillets, but we can also come in here and on these 2D holes, I can select the surface, specify a diameter threshold, and anything that is, smaller than this diameter threshold, it'll identify. So here it's identified these 4 holes where the diameter is smaller than my 10 diameter threshold, and I can delete out those holes to make my life easier for meshing. And why I wanted to save that one there for it didn't quite break here, but we'll see here that those bolt holes, if they're too small relative to the element size, they really tend to give you some low quality elements in either the aspect ratio or Jacobian. And here we're seeing that there's a good handful of my elements failing at that surface. So what I'm going to do is come in here, defeature at that surface, going to find and delete out those holes. And now if I come back into my checks, well, I don't have any failed Jacobians at that corner anymore. And I'm going to lower my Jacobian limit to be that 0.5. We're seeing it's a little bit better there. So some really good stuff there to help you with those quality checks. Now, for those of you with the initiative and the time and the know-how, what I would recommend to you guys maybe between now and our next session or a month from now when you got the time to sit down with this, want to come into my files here, I would highly recommend coming into your student exercise folder and getting familiar with in these chapter 2 and 3 folders, exercises 2A through 2D. The first couple geometry chapters are a lot of this topology review and cleanup review that we've seen here. And the meshing, really, those first 3 meshing exercises, A, B, and C, and we have the step-by-step guides for those in your student manual folder. I would really recommend taking the time to go through those at your own speed. It's going to be a lot of the same concepts I've talked about here. A lot of them use the same models. I kind of just combined a few of the exercises for our demos. But it'll give you another chance to see those at your own speed, gives you guys a chance to click through those at your own time. And while I'm really happy for you guys to have a chance to sit with myself and Darius these last couple of days to see some best practices and the right way to do them, there's no better way to learn these than trying them out for yourselves, though. I think I do a pretty good job. I'm going to toot my own horn a slight bit, but even better than me talking at you guys for as many hours as I can afford, really getting your hands dirty with yourself is the best way, in my opinion, to get familiar with these. There's no better way to learn how to mesh than to try it for yourself, screw something up or get through a challenging part. And once you do it a couple times here, your first meshes might not be perfect in the beginning, but you're going to be, as you get more comfortable with it, it gets a lot easier, and these questions really start to answer themselves for it. Now, one question I'm seeing come in, and this is a really good question for what we're ending on here today. What percentage of error is acceptable when we're thinking of quality check? And more so than thinking of this in terms of, you should have only 1% of your elements or less than that be failing, and as long as you have 99%, you're good to go. Rather than thinking of it in terms of that kind of breakdown, I would think of it, and I still do, I think of it as your meshes as only as high quality as its lowest quality element. An econ professor of mine once posed us a question. I think I was like 16 years old. I was probably a sophomore in high school. This guy told us, it was the funniest thing. I still think about it and laugh about it. I'm bringing it up here. That if we were all in a classroom together and a bear broke in and was going to eat us, you don't need to be the fastest person to get away from the bear. You just need to be faster than the slowest person in the room. The bear is only going to eat one of us. Morbid example, yes, but there's an important caveat there. You didn't need to be fastest. You just needed to be faster than the slowest guy. Your mesh is sort of the opposite. Your mesh is only as good as its worst element. Doesn't matter if 99.99% of your mesh rocks. If you have one really screwed up element, some solvers will literally not solve it, and they'll say, this mesh sucks. You have an element that totally failed my internal quality requirement. I'm not that good. So a better way to think of this is that your mesh is only as good as its worst quality element. And that's why a lot of these tools are actually built around to tell you the worst case scenario or the worst element for all of these checks. So if I come in here and I start going back to a warpage check again, when I click this button, not only does it tell me in the bottom corner that 0 of my 566 elements failed, but it also tells me that the worst warpage was only 2.27 degrees. So more than thinking of an acceptable error percentage of total failing elements, you want to make sure that every element is meeting some minimum requirement for a couple of those checks there. And as a good rule of thumb there, the first couple checks I'd be concerned with, or that I kind of taught myself to meet, were those warpage, aspect ratio, and Jacobian, along with a minimum and maximum edge length. And generally, if you can meet those 5 in a pretty solid way, I would expect you to meet all of the other checks there because they're so intertwined with one another. So I hope that kind of helped answer that question. And then with that said here, I don't want to talk you guys' ear off anymore. I know we're ready to end this day. What I do want to say is what we're going to look at on our final session together on Thursday is setting up these analyses, solving them in OptiStruct, or the implicit solver, and actually looking at the results using HyperView. And I think once we see the finished product, there'll be some good light bulb moments for a lot of us in the room.
Garrett, of course, fantastic job. There was one question about, can you show again how you extracted the mid-surface for, on the model that you have?
Yep, totally. Let's go back here. I'm going to pull up here exercise a 2C. 2C walks you through this one here. So our mid-surfacing tool is hiding in the geometry menu at the bottom down here. And I'm going to come over to my middle column of this geometry tool set, and we have a mid-surface tool hiding in that middle column here. How the mid-surface tool works is I'm going to click on one of the surfaces of a given solid geometry. So it's important that you know that you're starting with 3D CAD. I know that's obvious, but it'll get mad at you if you try to mid-surface already 2D stuff. So I'm going to select something on the volume. Now, HyperMesh automatically grabbed the rest of the solid because it knows it's an enclosed volume, so that's a good thing. It's kind of like a built-in check. Once I see that it's selected correctly, the only thing we need to do is just hit extract. Sometimes it asks you if you want to check something out. Say no. It's more trouble than it's worth. I'm happy to kind of meet with you privately to talk to you about plates, but we shouldn't have to. But once you're done with that extraction there, it's going to automatically set the solid you started with to be a transparent color. So I know it's tough to see here. Let me kind of close that. I do have the transparent solid, and it's going to bring that middle surface in for you as well. I typically make the transparent solid a white or gray color, and I'll set the middle surface to be something very bright like this yellow, because this allows me to come in here and review to kind of visually confirm that that middle surface that got extracted came out clean, it's located at the correct plane, and it's matching the curvature of the parent solid correctly. So it's a nice little built-in tool that it sets the visualization for you kind of in advance to help confirm that it came out cleanly.
All right. Again, thank you, Garrett. Awesome job. There's multiple compliments again today on what you've done, and I hope everybody shares the same feeling. Again, the training is really helping you understand how to approach things. While we might not go through every button click there is, but it allows you to feel much more comfortable with using the tool and then applying it to the prompts that you have and how to think a little bit big picture too. So again, we'll start the next session for HyperMesh and the final session on Thursday. Same time, 3:30. We, of course, start at 3:35 just to make sure everybody has a chance to get settled in at that point. So we look forward to having everybody there again. And thank you. Talk to everybody on Thursday. Bye.